Hi there, and welcome to the second video that I'm making over logistic functions for BC Calculus. To recap, what we did in the last video is we took the differential function, or the differential equation, I should say, of dp over dt was equal to kp times 1 minus p over L. And what we did is we took that differential equation and we found its general solution where we would say p of t was equal to kp times, nope, I'm just, my mind is wanting to just rewrite the differential equation. We had L over 1 plus c times e to the negative kt power. Well, in this case, in your notes, the way that they had it written is they had it written slightly differently, where they had it written as p of t is equal to L over 1 plus A times e to the negative kt power. Whoa, and I missed that completely. Negative kt power, where the c value, which is the constant that get introduced to the problem, and the a value, those are essentially the same. And here it's kind of explaining what the value or what each variable kind of represents. The capital L is the limiting factor of the problem. K represents the constant of proportionality, if it's you know increasing or decreasing, and A in this case depends on the initial population P naught, and we kind of find it by using that ratio there. So what we're going to be looking at now is we want to kind of look at some of the characteristics of a logistic function and see how we can kind of look at it on a graph. How do we interpret it? So the carrying capacity, L, is the maximum population that an environment is capable of sustaining. And again, just kind of piggybacking off what we did in the last video, is we kind of briefly explained that exponential functions, while they have a range of 0 to infinity, it's not possible to even come close to approaching infinity, because there's going to be natural environmental restrictions that are going to say, well, you can't have 78 quintillion people living on the planet because there's either not enough space, not enough food, something like that. So here, looking at the differential equation, we can interpret some values here. As p approaches 0, dp over dt, again the slope, that's going to approach k times p, which is essentially going to be kind of a constant. So in a lot of ways, you can look at it as kind of like a horizontal line, um, meaning that it has a slope of 0. But here specifically, we're going to say as p approaches L, as the population approaches the limiting limiting value, then the slope definitely is going to approach 0. And we'll kind of see what that looks like here in just a second when we take a look at the graph. So here we see on the left side of the graph, we very much, if the graph kind of got extended to say like -2, -3, something like that, you're definitely going to see how the slope is going to wind up being very kind of horizontal there. But it's not going to necessarily be uh, at 0. It's just going to be, or the slope is not going to be at 0, just like here. We're looking at here, I have a slope of 0 at whatever the limiting factor is. So down here, I'm going to kind of have a slope of 0 also when if we're looking at it, kind of like as an exponential function. We have the horizontal asymptote, and then it kind of goes up. Same thing here on the left side of the graph. So looking at it here, the graph of function p, this is our logistic curve. Logistic growth in the population grows fastest when the population is half of the carrying capacity. So here we're going to say that the max value of dp dt is as p approaches, or here is going to be when p is equal to half of the carrying capacity, or whatever L is divided by 2. Uh, to find the maximum rate of change, and this is going to be again at where the carrying capacity is equal to 1/2 of the overall or the population is equal to half of the carrying capacity. What we would say is we'd say 1 over k times the natural log of a. And what we're going to see here, I don't remember uh, where we had this function. Yeah, let's go ahead and add some stuff here. This dot that we have here, that is the, let me try and do this in another color so it's a little easier to see. This is our maximum slope. This is where it will be its biggest. So as you go from left to right, you can see the function, the slope is increasing, but uh, at that point, it's acting like a point of inflection. So we're changing from concave up to concave down, and we can see again our slope beginning to decrease over time. So this blue dotted line, this is our carrying capacity. So in this case, whatever the population is, it can't be more than 4 because the carrying capacity that says that's as far as you can go. And down here, all of this stuff down here, this is approximately exponential. Oops, can't spell exponential. Exponential. Okay, exponential. And the maximum slope where that occurs, that is going to be a point of inflection on the graph. Okay. So those are the characteristics of a logistic curve, and this particular one is increasing over time. You could have logistic curves that decrease over time, and they would be essentially like a vertical reflection of what you see there. Okay. Uh, oh, sorry about that. Somebody heard a car door slam, and they have to go investigate now. So here the slopes are small near where the population is 0 and where the population is going to be equal to as it approaches the carrying capacity. So when you have at the very beginning of the curve and at the very end of the curve, that's where your slopes are the smallest, where they're closest to 0. It is steepest at the point of inflection of the curve, where it changes from being concave up to concave down or vice versa, meaning that is half of the carrying capacity. And what happens if the population happens to be greater than the carrying capacity? Well, if you have a population that's greater than the carrying capacity, then the slope of your curve, they'll be negative, okay? And what that means is that your population at that point will be in decline. Now, one more thing real quick before we kind of move on. We talk about this a lot of times as far as uh, environmental systems, as far as how many people, animals, whatever could live in a system. But this is also very useful for uh, businesses, companies, where they can say, oh, as they introduce a new product, things get really interesting really quick, so it grows quickly. But at some point, it's going to hit that midpoint of the half of the carrying capacity. Now, what the carrying capacity is, we don't necessarily know for everything all the time. You have to kind of take a look and see. But you know, at that at that point here, if you're selling items, this is about where your maximum profit is going to be from them as far as how much money you could charge for it. So after that point, people are going to start buying less and less and less of it. So you might want to, put it on sale to reduce your inventory, things like that. Those are all characteristics of a logistic curve. So at the very beginning of the curve and at the very end of the curve, the slopes are very small. They're close to zero, and as you uh, approach your midpoint of the curve, for where your point of inflection is, that's where it's increasing the fastest or decreasing the fastest, and uh, you know the asymptotes that we have at the top and the bottom, for the top particularly, is where the carrying capacity of the function is going to be. Okay, so I'm going to wrap it up here for this particular video. The next one's going to be a little bit more involved as far as the work that you have to see, so I don't want to make this one too terribly complicated or too terribly long. So we're going to go ahead and pause here, guys. Thanks for watching. Take care and be good.